Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss the topic memory hierarchy. So already we know the digital computer system, it has different memory devices, and also a digital computer system mainly it has three functional parts that are central processing unit, shortly we can call the CPU, input and output devices, and the third component is a memory unit. So these are the three essential functional parts of the digital computer system. So now we are discussing about the memory. So memory unit is, we are discussing about the memory unit. So memory unit is, it is an essential component in any digital computer system, because the memory, so using this memory we are storing different programs and the data. So in order to store the different programs and data, we are using the memory unit. So a very small computer with a limited application may be able to fulfill its intended task without the need of additional storage capacity. So if you consider a small computer with a limited application, so a small computer with a limited application, it may be able to fulfill its intended task. But if you consider a small computer with a large application, so the computer may not fulfill its intended task, because for the large application it requires more memory capacity. Okay, so that's why a small computer with a large application, it may not fulfill its intended task because it requires some additional memory capacity. Okay, so that's why the memory unit plays a vital role in digital computer system. So most general purpose computers would run efficiently if they were equipped with additional storage beyond the capacity of the main memory. So here, so the main memory. So main memory is a limited memory, and the RAM. So RAM memory. So random access memory. So RAM can be considered as the main memory. Okay. So the main memory is a limited in size. Like we will use some 4 GB, 6 GB, 8 GB, like that. So it is a limited. So that's why we cannot store all the programs and data inside the main memory. Okay. So for that purpose, we have to use the additional memory device. So that are we can call auxiliary memory devices. So in that auxiliary memory devices, we are storing the programs and the data which are not needed by the CPU currently. Okay, so that the general purpose computer would run more efficiently if they equipped with additional storage capacity, and it is more economical to use low cost storage devices to serve as a backup for storing the information that is not currently used by the CPU. So only the programs and the data which is currently needed by the CPU only reside in the main memory, and whatever the programs and data not needed by the CPU currently, then all that we will be stored in the auxiliary memory. So in order to for the auxiliary memory, we are using a low cost storage devices, low cost, because for the auxiliary memory devices they are available in a large size, like some gigabytes, terabytes. So that's why, and their cost also low. So they are inexpensive. So the auxiliary memory devices are inexpensive, but whereas this main memory is expensive. Okay, so we are using a low cost storage devices to serve as a backup for storing the information that is not currently needed by the CPU. And a digital computer system, it consists of several memory devices like main memory, auxiliary memory, and cache memory. So like that. Okay, so the memory unit. So what is main memory? So main memory is the memory unit that communicates directly with the CPU. So directly it is communicating. The memory is directly communicating with the CPU. So that's why it is called main memory. So main memory. So main memory is the memory unit that communicates directly with the CPU. Okay, so that is called main memory. So, because the main memory is limited, so that's why we are using some auxiliary memory devices also. So what are auxiliary memory devices? So the devices that provide backup storage. So devices that provide backup storage that are called auxiliary memory. So auxiliary memory. So the most common auxiliary memory devices used in a digital computer system are magnetic tapes and magnetic disks. So these are the two commonly used auxiliary memory devices: magnetic tapes and magnetic disks, and also some hard disks. So these are all the different pen drives. So these are all different auxiliary devices. So here you can see how the physical structure will be there for magnetic tapes. So this is a magnetic tape. So using this magnetic tape, we can store some audio information. So using this magnetic tapes, we can listen only the audio. And coming to the magnetic disks. So the physical structure of the magnetic disks will be, you can see here. So magnetic disks. Okay. So using this auxiliary memory devices, we can store the information. We can store the programs and the data for future purpose. Okay. So using for this auxiliary devices can be used for to store system programs and large data files and other backup information. So this type of information we can store in the auxiliary memory devices. What type of information? So the files related to the system programs and large data files and other backup information. So these type of information we can store. And only the programs and the data currently needed by the processor reside in the main memory. And the programs and data which are not needed by the CPU will be transferred to the auxiliary memory. Okay, so why we are transferring the not required programs and data to the auxiliary memory? Because in order to free up the space of the main memory, because main memory is it is a limited in size, so that's why we are transferring the not needed programs and data to the auxiliary memory. Okay, so the memory hierarchy system, it consists of all storage devices employed in a computer system from slow but high capacity auxiliary memory. So these are the auxiliary memory. So the structure will be like this. Okay. So these are arranged in a hierarchy. So in the bottom, the two memory devices are auxiliary memory. So these auxiliary memory these are low cost. These are low. Okay. So these are slow but high capacity auxiliary memory. So these are low cost, okay, slow but high capacity, because these auxiliary memory devices, they are available some GBs and TBs, terabytes. Okay. To a relatively faster main memory. So after the auxiliary memory, we are using a main memory. To an even smaller and faster cache memory. So after that, you are using cache memory. So cache memory is the size of the cache memory is very small, it will be in some KBs or MBs, but it is expensive because the cost of the cache memory is very high when you compare with the auxiliary memory devices. Okay, so here the memory device of the digital computer system divided into 5 major hierarchies. That are these 5. So what are those? So register memory, cache memory, main memory, magnetic disks, magnetic tapes. So these are the 5 major memory hierarchy. Okay, from the bottom to the top. So magnetic tapes, magnetic disks, main memory, cache memory, and register memory. So these are the different memory hierarchy. So the processor can easily shift from one level to the another level easily based on its requirement. And if you look into the properties of memories, so properties. So basically every memory it is having some properties like storage capacity, cost per bit, access time. So these are the main properties of the memory. So what is the first one? Storage capacity. Storage capacity. So what is storage capacity? Storage capacity is the volume of that data that can be stored by the memory. So that is the storage capacity. Okay. So first one is a storage capacity. So storage capacity is a volume of data so that the system's memory can store. Okay, so that is a storage capacity. So here the one moves from top to bottom. So top to bottom. So the storage capacity of the memory will be increases because if you look into the register memory, so what will be the storage capacity of the register memory? It will be available in some bytes. So bytes or words. Only the registers it can store either bytes of information or words. So byte means a group of 8 bits, that is called 1 byte. So word means a group of 16 bits, that is called word. So only we can store either bytes or words of information only using the register memory. And after that, cache memory. So cache memory is it is available in the storage capacity of some kilobytes or megabytes. Okay. Next, main memory. So main memory, it is the storage capacity of the main memory is it is available in some gigabytes, GBs. And coming to the auxiliary memory, it is available in gigabytes or terabytes. So that means what will happen when you observe from top to bottom? So the storage capacity is increasing. The storage capacity is increasing. Okay, so that is a storage capacity. And second one is a cost per bit. Cost per bit. So because if you observe the cost of these different memory hierarchies, so the first one is the register memory because the registers are not available inside the processor. Okay, leave it. And next one is the cache memory. So the cache memory around it costs some 3,000 to some 4,000. Okay, but so it is available in KBs, but the cost is very high, 3,000 to 4,000. After that, if you come to the main memory, so main memory, it is available from 1,500 to 3,000. And auxiliary memory or hard disks, it is available in some around some 3,000 to 4,000. Okay, so suppose if you take 1 TB, it is available at 3,000 to 4,000 cost in between the range. Okay, so what will happen? So here the cost per bit is decreasing. The cost per bit because here in the auxiliary memories we have more storage capacity, but it costs very less. Okay, so that is a cost per bit. Next, third one is access time. So what is access time? So access time it refers to the time interval present between the request for ready or read and the data availability. So this is called the time interval between these two is called the access time. So the time interval between the request for read or write and the data availability, that is called access time. So as one moves from top top to the top to the bottom, the access time will be increases, because so the auxiliary memory devices are very slow. That means they need more access time. And cache memory, main memory. So cache memory and the main memory, it takes very less time to access the data because their access times are very less. Okay. So for the cache memory, for the cache memory, it takes 100 nanoseconds to access the data. So that means very fast. And the access time of the main memory is it will be 7 times the cache memory. So that means 700 nanoseconds. So that means the access time ratio of the cache memory to the main memory is 1:7. Okay. And coming to the auxiliary memory. So the auxiliary memory access time is 1000 times that of the main memory. So 1000 times that of the main memory. So that means it is the access time is very high. That means the auxiliary memory devices are very slow. Okay. So these are the access time. So these are the three main important properties of materials. So that are storage capacity, cost per bit, and access time. And this is a memory hierarchy in a digital computer system. So here you can see all the different memory devices associated with the digital computer system. So here you can see the CPU, Central Processing Unit. So the CPU is responsible to perform various operations inside the computer. So under the main memory, these are the auxiliary memory devices, and this is a cache memory. So these are the three memory devices associated with the CPU. So main memory, auxiliary memory, and the cache memory. So already we have seen main memory is the memory which can directly communicate with the CPU. That is called main memory. So main memory, it can be considered as RAM. So RAM can be considered as a main memory. And main memory, RAM. So RAM is a volatile memory. So what is volatile memory? Volatile memory is the data present in main memory will be there until the power is turned on. When the power fails, then the data stored in the main memory gets erased. So that is a main memory. So it is having the property of volatile memory. So its data will be present until the power is present. And on the other hand, auxiliary memory. So auxiliary memories are they are non-volatile memory. Non-volatile memory. So what is non-volatile memory? So even the power fades, the data stored in the non-volatile memory will be there, will be present. So will not get erased. Okay, so that is a main advantage with the auxiliary memory. Okay. So these are the examples of the auxiliary memory: magnetic tapes and magnetic disks. So these auxiliary memories, they are not directly communicate with the CPU. So they are communicating through the IO processor and the main memory. So suppose if the processor is needs some programs and the data to execute, so that required programs and data will be transferred from auxiliary memory to the main memory, and from the main memory the CPU will execute. So that is a process how the CPU will execute the programs and the data. Suppose if if the unused programs and data is available in main memory. So that unused programs and data will be transferred from main memory to the auxiliary memory in order to free up the space of main memory. Okay, so in this way only the required programs and data will be stored in the main memory, and unrequired programs and data will be transferred to the auxiliary memory. Okay, and coming to the Cauchy memory. So already we know the properties of the Cauchy memory. So Cauchy memory is it is small in size, that means small in storage capacity, but it is an expensive memory. It is expensive because the cost per bit is very high for the Cauchy memory. So why we are using Cauchy memory here? Because it is the Cauchy memory. It can be used to matches the speeds of the CPU and the main memory, because the CPU it can execute the instructions at a rate of million instructions per second. So that means at a very faster rate it can execute. That means the speed of the CPU is very high when you compare with the main memory. So there is a difference in their speeds. So that's why in order to match their speeds, we are in between them. We are using a Cauchy memory. So that is the use of the Cauchy memory. So how it will synchronize their speeds? See, so suppose if the CPU requires some programs and data, so the CPU first it will checks in the main memory. Okay, so if that program and data is available in main memory, then it will be taken from the main memory. It will be executed. Okay, suppose okay, after some time, if the same data is required by the CPU, then the CPU will not go to the main memory directly. So first the CPU will checks in Cauchy memory, because the Cauchy memory, when the CPU is accessing the data from the main memory, that portion of a copy of the data will also be placed in the Cauchy memory. Okay, so when the CPU requests that data again, then first CPU will checks in the Cauchy memory. If the data is available in Cauchy memory, then the CPU can access from the Cauchy memory. Otherwise, then only the CPU will go to the main memory and it will access from the main memory. So even that the required data is not present in the main memory, then it will go to the auxiliary memory. If it is available in the auxiliary memory, then that required programs will be transferred to the main memory. So in this way, the programs and data will be gets executed from the main memory. Okay, so this is about the memory hierarchy in a digital computer system. So the main memory occupies a central position by being able to communicate directly with the CPU and auxiliary memory devices through an IO processor. So already we have seen. So auxiliary memory devices are not directly communicating with the CPU because they are communicating through the IO processor. So what it will do IO processor? So the IO processor will perform the operations related to the input and output devices, like some reading the data from the device or sending the data to the device. And when programs not residing in main memory are needed by CPU, they are brought from auxiliary memory. And programs not currently needed in main memory are transferred to the auxiliary memory to provide space for currently used programs and data. And a special very high speed memory called Cauchy is sometimes used to increase the speed of processing. So already we have seen what is Cauchy memory, its properties, and why we are using. So why we are using Cauchy memory? Cauchy memory is using in order to increase the speed of the processing. Okay. And this Cauchy memory, it is employed in computer systems to compensate for the speed differential in order to compensate their speed differential between the main memory and the CPU. Okay, so the CPU logic is usually faster than main memory access time. So already we know the CPU speed is more than the main memory. So CPU, it can execute the instructions million instructions per second. So that means a million instructions per second means it is very high speed when you compare with the main memory. So with the result that processing speed is limited primarily by the speed of main memory. So a technique is used to compensate for the mismatch in operating speeds is to employ in extremely fast small cache between the CPU and the main memory. So as the storage capacity of the memory increases, so as storage capacity of the memory increases, so see here. So what is this? This is a memory hierarchy. Okay, so in this way, the storage capacity will be increases because the storage capacity for the register memory is small, and for the cache memory it will be little bit more than register memory. Main memory it will be little bit more than cache memory. So like that, the size will be increases gradually. Okay, so as the storage capacity of the memory increases, the cost per bit for storing binary information decreases. So this is a storage capacity. Storage capacity. Okay, so storage capacity will be decreases. Okay, so if the storage capacity increases, then the cost for bit will be decreases, and access time of the memory becomes longer. So the access time becomes longer because for the auxiliary memory devices, the access time is very high because 1000 times that of the main memory. Okay, so the overall goal of using memory hierarchy. So we have seen what is a memory hierarchy. So in memory hierarchy, we have different memory devices are there. So what is the main overall goal of this memory hierarchy? In order to obtain the highest possible average access time, average access speed. So this is a goal of the using the memory hierarchy. So while minimizing the total cost of the entire memory system. So auxiliary and memory cache memories are used for different purposes. The cache holds the parts of the program and data that are most frequently used. So if you look into the cache memory, so why we are using cache memory? So cache memory is used to store the data, the frequently used data. So that means already we have seen in previous slides. Okay. So okay, while the auxiliary memory. So auxiliary memory, it holds those parts that are not presently used by the CPU. So only the data needed by the CPU will reside in the main memory, and the programs and the data not needed by the CPU will be stored in the auxiliary memory. So for that purpose, we are using the auxiliary memory. So the purpose of using auxiliary memory is for backup purpose. So as a backup, we can you store some system related programs, large data files, and other backup information. So all that we can store in the auxiliary memories. Moreover, the CPU has direct access to both cache and the main memory. So, okay, but not to auxiliary memory. So the CPU, it can directly access only the main memory and the cache memory, but not auxiliary memory. Because the auxiliary memory, it is connected through the main memory and the IO processor. So the transfer from auxiliary memory to main memory is usually done by means of DMA, direct memory access of large blocks of data. The typical access time ratio between the cache and the main memory is 1 to 7. Okay. So see here, for example, a typical cache memory have an access time of 100 nanoseconds. So this is a access time of the cache memory. Cache memory. So it is the cache memory is a very faster. Okay. So after that, after the cache memory, the fastest memory is the main memory. So main memory. So what is the access time of the main memory? That is a 700 nanoseconds. Okay. So access time 700 nanoseconds for the main memory. And auxiliary memory average access time is usually 1000 times that of the main memory. So that means the auxiliary memory devices are very slow. And if you come to the block size, so block size in auxiliary memory typically range from 256 to 2048 words. Okay. While the cache block size is typically from 1 to 16 words, because the cache memory is it is very small when you compare with the auxiliary memories. So many operating systems are designed to enable the CPU to process a number of independent programs concurrently. So with the CPU, we can perform multiple tasks simultaneously. So that is called multi-programming. Multi-programming. So it refers to the existence of two or more programs in different parts of the memory hierarchy at same time. In a multiprocessing programming system, when one program is waiting for input or output transfer, there is another program ready to utilize the CPU. So that means here two or more tasks are sharing the CPU's time. So in this way, we can perform two or more tasks simultaneously. So that is called multi-programming. And the computer programs are sometimes too long to be accommodated in the total space available in main memory. So already we know, as we know, the main memory is limited. Like we are using a 4 GB or 6 GB or 8 GB. So we cannot accommodate more programs and data inside the main memory. Because suppose if you consider a example, so you are watching a movie. So suppose if you are watching a HD movie, then the size of the movie will be around some 10 GB or 8 GB like that. Suppose if you are using a 6 GB RAM, then how that movie can store into the main memory? Here, the entire movie will not be loaded into the main memory at a time. Only that particular duration of the video that particular segment of the video will be loaded into the main memory, and from that main memory it will be executed. So the data or entire movie will not be loaded into the main memory. Okay, so that is a concept here. So when the program or a segment of the program is to be executed, so when a program or the segment of the program is to be executed, it is transferred to the main memory to be executed by the CPU. It is a task of the operating system to maintain in main memory a portion of this information is currently active. The part of the computer system that supervises the flow of information between auxiliary memory and the main memory is called memory management system. So always here there is a transfer of information from the auxiliary memory to the main memory. So this process of transferring information from auxiliary memory to the main memory is called memory management system. So a digital computer system, mainly it has three functional parts: central processing unit, input and output devices, and memory unit. So these are the three important functional parts. So the memory is it plays a vital role in digital computer system, because Using the memory, we are storing some programs and the memory, programs and the data. So, digital computer system, it has different memory devices like main memory, auxiliary memory, and cache memory. So main memory is it is a central storage unit. Main memory is the central storage unit because from the main memory only the programs will be executed. So that's why the main memory is considered as the central storage unit in a digital computer system. So it is a relatively large and fast memory used to store programs and data during the computer operation. So it is relatively large because the size of the main memory, it is in the some gigabytes, and it is a faster memory. That means it has very less access time when you compare with the access time of the auxiliary memory. So the access time of the main memory is around some 700 nanoseconds. 700 nanoseconds. So that's why the main memory is having a large storage capacity and it is faster. And the principal technology used for the main memory is based on the integrated semiconductor integrated circuits. So the principle we are using in the main memory is the semiconductor integrated circuits. So RAM is a part of computer's main memory which is directly accessible by CPU. So RAM can be considered as the main memory. Okay. So integrated circuit RAM chips are available in two possible modes, that are SRAM, means static RAM, and second one is the dynamic RAM. So these are the two possible forms of the RAMs. One is the static RAM and another one is the dynamic RAM. So what is static RAM? So static RAM consists essentially of internal flip-flops. So it is designed using the internal flip-flops and that store the binary information. So that store the binary information. That means binary information is nothing but zeros and ones. So zeros and ones. So that is a binary information. So that we can store in the static RAM. And the stored information remains valid as long as the power is applied to unit, because the RAM. So what is the property of the RAM? RAM is it is a volatile memory. Volatile memory. So what is volatile memory? So the data stored in the memory will present only until the power is supplied. When the power supply is turned off, then the data stored in the memory will get erased. So that is a RAM memory. So that's why. So in the static RAM cells, only the data is present until the power is supplied to it. Coming to the second form of the RAM, that is a dynamic random access memory. So it stores the binary information in the form of electric charges. Electric charge that are applied to capacitors. So the capacitors are provided inside the chip by MOS transistors. So here we are using the DRAM, the dynamic RAM. It is designed using the MOS transistors. Okay. So these capacitors are provided inside these MOS transistors. Because so the stored charge on the capacitors tends to discharge with time. Okay, because with respect to the time, the charge stored in the MOS transistor will gets discharged. Okay, so and the capacitor must periodically recharged by refreshing the dynamic memory. So in the dynamic memory, we need to apply a refreshment cycle in order to store the data inside the memory cells. Okay, so these are the two different forms of the RAMs. First one is a static RAM and second one is a dynamic RAM. So here you can see how the DRAM cell, DRAM cell and SRAM cell will be designed. So this is a DRAM cell. So this DRAM cell, it is implemented using one pass transistor and one capacitor. And typical SRAM cell, it is designed with 6 MOS transistors. 6. So these are 1, 2, 3, 4, 5, 6. So in order to implement this SRAM cell, we require 6 MOS transistors. Okay. So if you compare the SRAM and DRAM, so SRAM has lower access time, so it is faster compared to the DRAM. So SRAM has lower access time. DRAM has higher access time. So it is slower than SRAM. Second one, SRAM is costlier than DRAM. So in order to implement or design SRAM, we require 6 MOS transistors for each memory cell. So that's why the SRAM is costlier and expensive when compared with the DRAM. And DRAM is costs less compared to the SRAM because here we require less number of components in order to implement the DRAM cell. Okay. And third one, SRAM requires a constant power supply, which means this type of memory consumes more power. Okay. So because here the power consumption is directly proportional to the number of components. Because here in the SRAM more number of components are there. That's why they consume more power. Okay. And DRAM offers a reduced power consumption due to the fact that information is stored in the capacitor. And fourth one, due to complex internal circuitry, less storage capacity is available compared to the same physical size of DRAM memory chip. And fifth one, SRAM has low packaging density and the DRAM has high packaging density. So these are the difference between the SRAM and the DRAM. So the RAM is used for storing bulk of programs and data that are subject to change. Okay. So because the RAM is a temporary storage device. It is not a permanent. So temporary storage memory. So that's why the programs and data that are subject to change. So that is a RAM. And also the RAM is a volatile memory. So that's why the data present in the RAM will be erased when we turn off the CPU. And coming to the ROM, read-only memory. So it is used for storing programs that are permanently residing in the computer. Okay. So the programs and data that will be stored in the ROM will be reside for a long duration. Okay, that means the ROM can be used to store the programs and the data as a permanent. So the ROM portion of main memory is needed for storing an initial program. So here we have the program is called Bootstrap Loader. So Bootstrap Loader is a program that is used to start your computer at a very first time. So when you turn on the CPU, then this Bootstrap Loader program will run from your from the main memory. Okay. So what is the Bootstrap Loader program? Bootstrap Loader program is a program whose function is to start the computer software operating. Okay. So it will start the computer's software operating when power is turned on. Okay. So this Bootstrap Loader program, it will be stored in the ROM. Okay, it will be stored in the ROM. But the bootstrap loader program, it will be run from the RAM. It will be run from RAM. So here you have a doubt that why can't we store this bootstrap loader program in the RAM memory itself? Because if you store the bootstrap loader program in the RAM memory, so we have a problem, because when you load this bootstrap loader program into the RAM memory, okay, so when you turn off your computer, the bootstrap loader program which is stored in the RAM memory will be gets erased. So when you turn on the computer next time, the bootstrap loader program will not execute, because that bootstrap loader program erased from your RAM memory. Okay, so in order to overcome this problem, we are storing the bootstrap loader program in from the ROM memory. We are storing in the ROM memory. But this the program, the bootstrap loader program which is stored in the ROM memory, it will be copied to the RAM during execution. Okay. Okay. So since the RAM is volatile, its contents are destroyed when power is turned off. Power is turned off. So the contents of the ROM remains unchanged after power is turned off and on again. So that's why we are storing the bootstrap loader program into the ROM, and that bootstrap loader program will be executing from the RAM. So this is a reason why we are not storing the bootstrap loader program in the RAM memory. And the startup of computer consists of turning the power on and starting the execution of an initial program. Thus, when power is turned on, the hardware of the computer sets the program counter to the first address of the bootstrap loader. The bootstrap program loads a portion of the operating system from disk to main memory, and control is then transferred to the operating system, which prepares the computer for general use. So the RAM and ROM are available in different varieties of sizes, because we have some different RAMs, 512 RAM, 256 RAM, 128 bytes of RAM. Similarly, ROM 512 kilobytes, 512 bytes ROM. So like that, we have different sizes of the memories. So if the memory needed for the computer is larger than the capacity of one chip, so it is necessary to combine a number of chips to form the required memory size. Suppose I want 512 bytes of, so I need 512 bytes of ROM, but I have 128 bytes of ROM chips. So what should I do? So I can combine these 128 bytes of ROM in order to form 512 bytes of ROM. So how I can use? So see here. So I can use 128 bytes of ROM chips. So if I combine 4 chips, then that is equal to 512 bytes of ROM. Okay. So in this way, we can combine one or more memory chips in order to form the required memory size. So you can better understand this with an example of 1024 by 8 memory can be constructed. So I am going to construct 1024 by 8. Okay, so this 1024, it represents the number of memory locations. And this 8, it represents the word size of every memory location. So I am going to construct 1024 by 8 with 128 by 8 RAM chips and 512 by 8 ROM chips. So 128 by 8 RAM chips are there, and 512 by 8 ROM chips are there. So how I can combine, and how many number of chips I can use? So already here 512 by 8 ROM chips are there. So here 128 by 8 RAM chips are there. So I can use four numbers. So if I use 128 by 8 RAM chips and 512 by 8, then that is equal to 1024 by 8 memory. So in this way, by combining one or more memory chips, we can form the required memory capacity. So RAM and ROM chips. So a RAM chip is better suited for communication with the CPU. If it has one or more control inputs, that selects the chip only when needed. Another common feature is a bidirectional data bus that allows the transfer of data either from memory to CPU during the read operation or from CPU to memory during the write operation. Okay. So a bidirectional bus can be constructed with three-state buffers. So see here. So here you can see the block diagram and functional table of RAM chip. So we have seen we have different memory chips are there. RAM memory chip, ROM memory chip. So this is a RAM, random access memory. Okay. So the size of the RAM chip is 128 by 8 RAM chip. And here the inputs are CS1, CS2 bar. So CS inputs are, CS means chip selection. Chip selection. So suppose if you have more number of memory chips, then using this chip selection inputs, we can choose or we can select a particular memory chip. Okay. So chip selection 1, it is active high, and chip selection 2, it is active low. So the bar upon the CS2, it represents active low. So active low means it will be activated when the input is active low. CS1, it is active high. That means if the input is logic high, then only the memory chip will be activated. And read write. So because with the RAM memory, random access memory, we can perform either memory read operation or memory write operation. So read and write. And 128 by 8. So that means how many memory locations are there? So this 128 by 8. So this we can write 2 power n into m. So this is a representation of the memory. So what is n here? Where n is the number of address lines. Okay. So here n is equal to 7. N is equal to 7. So 2 power 7. So that is equal to 128. So that means how many address lines are required? 7 address lines. So that's why 7 address lines. 7-bit address. And this 8. So what is this 8? This 8 is it represents the word size. So that means so total the memory structure will be like this. So starting location is a 000. Next 001, 002. So last location is a 127. So that means total we have 128 memory locations. So what is this 8? What is the memory word? So memory word is the number of bits we can store in each memory location. So here 1 0. So that means this is a one word. So that means one word we can store in this each memory location. Okay. So this is a block diagram of the RAM chip. If you look into the functional table here we have CS1, CS2 bar, read, write. Okay. So this memory chip will be activated only if CS1 is equal to 1, CS2 bar is equal to 0. Other than these two inputs, the memory chip will be in inhibit mode. That means it will be in inactive mode. So see here. So CS1 is 0, CS2 bar 0. So what will be the condition for in order to activate the RAM chip? 1 0, but here 0 0. So under whatever inputs you apply to the read or write, then the memory it will perform inhibit operation. So when the memory is in inhibit operation, the state of data bus will be high impedance. High impedance means neither low nor high, in between. Logic low and logic high. And the second one 0 1. So CS1 0, CS2 bar 1. So this is also for this case also the memory chip will not be in active mode. This is also inhibit. And for CS1 and the third case 1 0. So 1 0. So if CS1 is equal to 1, CS2 bar is equal to 0, then the memory chip will be active. So here. So if it is active, then we can perform either memory read operation or memory write operation. So suppose if you want to perform write operation. So write, okay. So see here. So 1 0 is there. So read and write both are logic 0. So that means the memory will be in inhibit mode. Okay. And next case 1 0. Here in the next case we are performing write operation because at write bar we have 1. It performs write operation. Suppose if the read bar signal is equal to logic 1, then it performs read operation. And if both the chip selection lines are equal to logic 1, then in this case also it will perform inhibit, high impedance. Okay, so this is a block diagram and functional table of the RAM. So read and write inputs are sometimes combined into one line labeled read or write. When the chip is selected, the two binary states in this line specifies the two operations are read or write. So here it is mentioned with read or write bar. So if it 0. So if read or write bar is equal to 0, then it performs write operation. So if the read or write bar is equal to 1, it performs read operation. So in this way, it performs either memory read operation or memory write operation. The unit is in operation only when CS1 is equal to 1 and CS2 bar is equal to 0. So already we have seen. So for this case, if the chip selection inputs are not enabled, or if they are enabled but the read or write inputs are not enabled. Okay. So already we have seen all these cases in this table. Okay. So coming to the ROM chip. So till now we have seen how the RAM chip will be there and the different inputs for the RAM chip. So ROM chip is organized actionally in a similar manner. ROM can only read. So read only. So as the name it suggests, read only memory. That means only we can perform a read operation with this ROM chip. We can perform only the read operation. The data bus can only be in an output mode. Okay, so reading. So output mode. But if you see the previous one, RAM memory. So RAM memory, what will be the direction of the data bus? It will be a bidirectional because with this RAM memory, we can perform either memory read operation or memory write operation. Okay, so the 9 address lines. So what will be the size of the ROM? It will be 512 by 8. So already we have seen. So how the memory chip size will be represented? 2 power small n into capital M. So where n is the number of address lines, where capital M is the word size. Word size. So n is equal to address lines. Okay. So that means 2 power 9 into 8. So now tell me, so what are the number of address lines required? 9 address lines. So that's why a 9-bit address is there. Next. And here also we have 2 chip selection lines. CS1 and CS2 bar. Okay. So 9 address line in the ROM chip specify any one of the 512 bytes stored in it. So memory, it will be here. So 0. So starting will be 0, 1, 2 up to 5, 1, 1. Because memory location, the address is started represented with 0 initially. So that means the last memory location is a n minus 1, 512 minus 1, 511. Okay. So the 2 chip selection inputs must be CS1 should be 1 and CS2 bar is equal to 0 for the unit to operate. Otherwise, the data bus is in high impedance state. There is no need for a read or write control because the unit can only read. So here we don't have any read or write signals because with this particular ROM chip we can only perform the read operation. Next, coming to the memory address map. So the designer of a memory computer system must calculate the amount of memory required for the particular application and assign it to the either RAM or ROM. Suppose if you are designing any computer system, we need to specify what size of memory we require. Okay, so that the memory we are implemented using RAM and ROM chips. The interconnection between memory and processor is then established from the knowledge of size of memory needed and the type of RAM and ROM chips available. The memory address map is a pictorial representation of assigned address space for each chip in the system. So here we are going to see a memory address mapping. So what is this memory address mapping? Memory address mapping is a pictorial representation of the address space, address range for each particular memory chip. So to demonstrate with a particular example, assume that a computer system needs 512 bytes of RAM and 512 bytes of ROM. Okay, so we are going to design a computer system with 512 bytes of RAM and 512 bytes of ROM. Okay, so the memory address map for this configuration is you can see here. So this is a address mapping for the computer. Okay, so what we are going to form? So 512 bytes of RAM, 512 bytes of ROM. But what sizes of RAM and ROM chips are available? So the available chips are 512 bytes of ROM is available, and 128 bytes of RAM chips. So with 128 bytes of RAM, suppose if you want to implement or if you want to form a 512 bytes of RAM, then how many number of RAM chips are required? We require 4 chips. We require 4 RAM chips, 4 128 bytes of RAM chips. So 4 into 128 bytes, that is equal to 512 bytes. So that means we require 4 RAM chips. So RAM 1, 2, 3, 4. So RAM 1, 2, 3, 4. So what is the address range for the first RAM 1? So 0002 to 007F. So that is the hexadecimal address. So these are the address bus. These are the address bus. Because 512 plus 512, so total 1024 bytes. So we require 10 address lines. So 1 to 10. So for the what is the size of the RAM 1? What is the size of the RAM 1? It is 128 bytes. So 128 bytes. So what is the number of address lines required? The number of address lines required 2 power 7. 2 power 7. So 7 address lines. So 1, 2, 3, 4, 5, 6, 7. Okay. So that means the starting address. Starting address is all zeros. So here X represents. What is X? X represents either 0 or 1. Okay. Okay. So starting address will be all zeros. Starting address will be all zeros. Ending address will be all ones. So this is for RAM 1. So what is its equivalent hexadecimal value? 0, 0. Starting address. What is the ending address? 4 ones. 4 ones means F. So here 111. 111 means 7. Okay. This is for 10 address lines. Suppose if you consider 16 address lines, then you can add zeros here. So starting address is all zeros and ending address is 007F. So in this way, we can find out the hexadecimal address. Okay. Next, similarly, RAM 2, RAM 3, 4. Okay. So, but here, how the CPU can select that particular RAM chip? Okay. So, from 1 to 7, it represents the number of memory locations. But 8 and 9. So 8 and 9 address lines are used to select the RAM chip, because we have 4 RAM memory chips. We have 4 RAM memory chips. So in order to select, so based on the address line 8 and address line 9, we are selecting the RAM chip. So when 8 and 9, 00, when 00, okay, so when 8 and 9 are 00, then RAM 1 will be selected. When 8 and 9 are 01, RAM 2 will be selected. When 10, RAM 3 will be selected. When 11, RAM 4 will be selected. So in this way, we can choose a required RAM memory chip. Okay. So, but here we have to decode the 8 and 9 address lines in order to select that particular RAM chip. And coming to the ROM, so how we can differentiate the RAM and ROM? So if the 10th address line, if the 10th address line is 0, then it will be a RAM chip. The 10th A10 address line, if the 10th address line is equal to 1, then it will be ROM. So in this way we are differentiating the RAM memory chip and the ROM memory chip. So this is a address map for the microcomputer. So the small x under the address bus line designate those lines that must be connected to the address inputs in each chip. So the RAM chips have 128 bytes and need 7 address lines. So 128, so that means 2 power 7. So 7 address lines are required. And the ROM chip size is 512 bytes. 512 means 2 power 9. So 9 address lines required. It is now necessary to distinguish between 4 RAM chips. So already we have seen how we can differentiate by decoding A8 and A9. By decoding this A8 and A9 address lines, then we can choose. Okay. So done with another bus line. Here choose line 10 for this purpose. Okay. So how we are choosing whether RAM chip or ROM chip? If the 10th line is 0, then it is a RAM chip. If the 10th line is equal to 1, it is a ROM chip. So the first hexadecimal digit represents the lines 13 to 16. Okay. So this one is always 0. The next hexadecimal digit represents lines 9 to 12. 9 to 12. But lines 11 and 12 are always 0. Okay. So the range of hexadecimal address for each component is determined from the x's associated with it. So x represents the binary number that can range from an all zeros to all ones. Okay. So memory connections to CPU. So RAM and ROM chips are connected to CPU through the data and address buses. Suppose if you want to connect any RAM or ROM chips, then we are connecting it to the CPU through the address bus and the data lines. So data lines are used in order to carry the data information, and address lines are used in order to carry the address information. So the low order lines in the address bus select the byte within the chips, and other lines in the address bus select a particular chip through the select chip selection inputs. Okay, so see here. So these 1 to 8, 1 to 7. So these are the lower order address lines. So these lower order address lines are used to in order to select that particular memory location. Okay. In order to select a byte within the chips, and the remaining address lines are used for the selection purpose. In order to select that particular chip, or in order to decide whether we are selecting the RAM chip or ROM chip. So the connection of memory chips to the CPU, you can see here. This configuration gives the memory capacity of 512 bytes of RAM and 512 bytes of ROM. So each RAM receives 7 lower order bits of the address bus to select one of the 128 possible bytes. Because here 128 bytes, that means you repeat 2 power 7. So total 7 address lines are required in order to select each byte. and the particular RAM chip is selected is determined from the lines 8 and 9. So this is done through 2 by 4 decoder. So using 2 by 4 decoder, we are selecting the RAMs. So when 8 and 9 lines, based on the 8 and 9 lines, we are choosing the RAMs. 0, 0, 0, 1, 1, 0, 1, 1. Suppose if this is 8 and this is a 9. So this will be RAM 1, RAM 2, RAM 3 and RAM 4. So in this way we are selecting the RAMs. So address bus lines 1 to 9 are applied to the input address of the ROM without going through the decoder. This assigns addresses 0 to 512 RAM and 512 to 1023 to ROM. So you can understood this with this memory connections to the CPU. So this is a CPU. So from the CPU we have a data bus, write signal, read signal, and we have a address bus. So the size of the address bus is a 16-bit address bus. So see here. So total we have 4 memory RAM chips. RAM chip 1, RAM chip 2, RAM chip 3, RAM chip 4, and the ROM. So the size of every RAM chip is 128 by 8. So that means by combining these 4, we will form 512 bytes. With this 512 bytes. So total we can have 1024 bytes by combining this one and this one. So see here. So the write bar signal is connecting to the all write bar signal of the all memory RAM chips. Here RAM, write, and similarly read signal also we are applying to all the RAM chips. We are applying a read signal to all the RAMs. Read and write signal we have applied to all the RAM chips. Now see here. So how we are see address lines 1 to 7. Address lines 1 to 7 directly we are applying to the all the RAM chips. So 1 to 7. So we are applying to first RAM, next second RAM, third RAM, next fourth RAM. And here now we need to distinguish the RAM chips, whether we are choosing RAM 1, RAM 2, RAM 3 or RAM 4. So how we can distinguish? By decoding the address lines 8 and 9. So by decoding address lines 8 and address lines 9, then we can select a particular RAM chip. So suppose based on the 8 and 9, we will select the RAM chip. So what is the output of the decoder? We have 4 outputs. Output 0, 1, 2, 3. So we have 4 RAMs. So output of each decoder, this 0 output of the decoder, we are connecting to the CS1 of RAM 1. Similarly, 1 output of the decoder we are giving to the CS1 of RAM 2. Similarly, 2 output of decoder we are giving to the CS1 of third RAM. Third output of the decoder we are giving to the CS1 of RAM 4. So CS1 is clear. Next, CS2 bar. So 10th pin, 10th address line. So 10th address line it is used to distinguish the memory chip, whether we are using a RAM chip or ROM chip. So for that purpose, so 10th address line, we are giving directly to the CS2 of RAM 1, RAM 2, RAM 3, similarly RAM 4 also. But the 10th address line, we are applying to the ROM memory chip through the NOT gate. Through the NOT gate. Okay. So now CS1, CS2, all clear. So, okay. Okay. So we have given. So under 8 and 9s of address lines from the CPU, we are giving directly to the ROM chip. Okay. And see here. So these address lines. So from the CPU, we have a data bus. So all the data bus of the all memory chips we have connected to the CPU. And this for the data bus of ROM chip also, we are connecting to the data bus of the CPU. Okay. So this is a memory connection to the CPU. Okay. So finally, by after completion of all these connections between the memory chips and the CPU, so it will form a total size of 1024 bytes. We can use 1024 bytes. Okay. So in this lecture, we have seen about the main memory. So main memory means RAM can be considered as a main memory. So in this lecture, we have seen different memory chips, RAM and ROM, and how we can combine different memory chips in order to form the required memory size. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.